Hello. Hi, everyone. I'm Sai Tagarwal. I'm a master's student here at the University of Illinois, Chicago. I've taken a course in cloud computing, and this is the walkthrough of its homework tools. Sorry, I was sore in my mouth and did not speak properly, but I'll try to convey as much as I can. Let me navigate to my project repo. So, in this project, we'll be simulating the man in the middle attack. In this, an attacker who is an insider deploys a service. The service may provide some useful functionality. The service then observes the communication paths, and based on these paths, the attacker identifies machines with valuable data and tries to capture them. To prevent such attacks, the organization might introduce modifications to the system. They can add honeypots. Honeypots are machines which act like they have valuable data, but if the attacker tries to capture them, the system would get alerted and the attacker would be neutralized. In this homework, we would simulate such an attack. Now we would use a large graph to represent such a system. To generate a random large graph, we would use Professor Mark Resnick's NetGame Sim. The NetGame Sim program generates a random graph and then adds perturbation to it using controllable parameters. The output of the NetGame Sim program includes the binary of the original graph, the binary of the perturbed graph, and the set of perturbations added to the original graph. Here, the original graph would represent the attacker's knowledge of the actual system, and the perturbed graph would represent the altered system, which includes modifications such as honeypots. Now, to simulate such an attack, we would conduct random walks. These random walks would represent communication paths observed by the attacker's service. Now, based on these paths and the attacker's knowledge of the original graph, the attacker's goal is to correctly identify the nodes with valuable data in the changed graph. This, is, this program in- simulates such an attack and outputs different statistical metrics on the attacks performed. The program is based on Spark to achieve high parallelism across multiple computing nodes. Now, coming to the first part of the program, is graph serialization. Now, the NetGame sim is developed using Scala 3 and outputs the graphs in binary format. However, Spark does not support Scala 3. Now, to incorporate the graphs into the program, I've written another project to convert the binary graphs into JSON graphs. These JSON graphs would be then uh, utilized by the main Scala 2 project. The graph serialization project is added to this repo in the graph serialization folder. Now I'll navigate to the graph serialization folder I have in my local machine and give a quick demo of how the graph can be converted to JSON. Now this is the graph to JSON project which converts the binary graph to the JSON format graph. I'll navigate into its project directory and create a jar of this project using spt clean something. Uh, this program will take two inputs, the uh, binary of the original graph, the binary of the perturbed graph, and will output the JSON format the original graph in the JSON format by the graph into the current directory. We see that the compilation has been completed, and we can go in the targets folder to find our jar file. I'll quickly uh, I'll quickly get these are the uh, binary graphs generated by the NetGameSim program. I'll quickly copy them and put them into the current directory, so it's just easy for me to demo it. I'll open up the terminal. I'll execute the jar file and give the paths to the two graphs in arguments. The jar has finished executing, and we can see that it has produced two JSON files. These include the JSON format graphs for the original and the perturbed graphs. Next, we'll come to the main project. This project will take the uh, JSON graphs uh, we just saw. It'll take three inputs. It'll take path to the original JSON graph, path to the perturbed graph, and also take uh, in third input, which would be the path to the directory in which all the program outputs will be stored. Now, these three inputs can be either given using the command line interface as arguments, or they can be given by the config file. If they are given by both, then the uh, command line values would take precedence over the config values. Now, this is a project I've set it up in local. Uh, and here is my config file. Uh, the first three parameters are the different three paths the program requires, which we just discussed. They can be either given the command line arguments or through here. The next are set of parameters which are used in different parts of the program. Now I've already given I've included sample data in my project repo. It includes the JSON of the original departed graph. I've added paths to those. And the uh, uh, path to the output directory is here. I'll delete the previous outputs. So we can run this again and see the outputs being generated. Let me make sure that I have not given any command line arguments. Okay. I'll go ahead and run the program. Our program is finished running. Once the program finishes running, it'll produce two YAML files. One is the SimScore YAML file. This file will include all the valuable nodes in the original graph, and the corresponding nodes in the perturb graph along with the SimScore, along with the maximum SimScore. The other YAML program output YAML will include the different statistics of the attacks performed. It will also include information about the original perturb graph. This I will make the jar of the main project and deploy it on AWS EMR. So navigated to the root of my project directory. I'll open the terminal and do spt clean file assembly just like before. Now, while this is running, we can navigate to the S3 and set up the required inputs which will be utilized by this program. Now, in S3, I'll create a new folder for the inputs. I'll create a new folder for the program output. Now, in the inputs folder, we'll need two files. That's the JSON of the original and the JSON of the photograph. I'll go ahead and upload those. I have those in my sample data. I will get back and see if the first it has run all the tests. Now all the tests are passed. Meanwhile, we can start with creating a cluster where we'll deploy our jar. We only need Spark and Hadoop for this program, so I'll remove the other ones. Now here I create a custom step. We want to use Spark application. Let's call this custom step. We can run it in either cluster mode or client mode, but because the main driver and the worker machines in the same network, client mode would be better here. We'll go back and see it's still taking time. You can give the path to the child later. Meanwhile, we can give the arguments. Now, this program takes in three arguments. One is the path to the original graph. I'll copy its path from here. Next, we need the path of the perturb graph. And lastly, we need the program output directory, which we created earlier. We'll get our outputs in this directory. Let's copy its URL to. You can see that the jar has been made. I'll navigate to my project folder. In this the target, there is our project jar. I'll upload this on the S3. This is a fat jar and includes all the dependencies. So we'll just have to run this. We shall take its path and add it to the Spark application job. That's all we need. I can save this step now. I would like to put logs in the, I don't want a new bucket for the logs, so I'll just delete this and I'll go back to my homework directory and add a new folder for logs. Let's take its path and give it here. Now I have already created the EMR and EC2 roles with the right permissions. I'll just add them and we'll go ahead and create the cluster. Now, while the cluster is instantiating, I can go back and talk more about my project. Now, to simulate a man-in-the-middle attack, the program first performs multiple parallel random walks using Spark. The number of parallel random walks can be specified by the number of parallel walks parameter in the config file. These walks would continue either until a node is reached which has no outgoing edge, or the maximum steps per walk has been attained. This parameter again can be set in the config file. Now, once all the random walks are completed, they are condensed into one graph. Next, a SimRank algorithm. The SimRank algorithm is applied on the traverse perturb graph and the original graph. The similarity score is calculated between each combination of valuable node in the traverse perturb graph and each valuable node in the original graph. All these scores are stored in the sim_scores.yaml file in the output directory. Next, if in the config parameter, we also specify another parameter called the attack threshold. Now, if the sim score between two nodes is more than this attack threshold, an attack is simulated. But the attack is successful if the node ID is able to node match. Still bootstrapping. Now I can go through the output of the program. This program outputs different parameters associated with its execution. First thing it tells us about is the number of nodes in the original graph and the perturb graph. In the example we are using, the original graph has 3001 nodes and the perturb graph has around 2988 nodes. Now, because of these perturbations, some valuable nodes would be removed as well. So SAML file also provides the details about the different perturbations. This is right here. Now this includes honeypots. These are the nodes added, which mimic like they have valuable nodes. Some nodes which have valuable data are also modified, and then some nodes can be removed too. I've deliberately increased the perturbation coefficient in the NetGensim program to get different variety of changes on the valuable nodes. Next, the output also contains different information of the random walks performed. It provides information of the minimum number of steps in the random walk, maximum number of steps in the random walk, medium number of steps in the mean steps. It also gives information about the percentage of nodes covered using these random walks. Next, if the similarity score is above the attack threshold and attack is simulated, the output YAML shows different information about these attacks performed. It shows the total attacks performed, shows the successful attacks on modified nodes. It attacks shows the total successful attacks performed, and then shows the attacks on modified nodes. Also, uh, while uh, doing these random walks, there's a possibility that a valuable node was explored, where it was not attacked because its maximum similarity score was below the attack threshold. Those nodes are also specified in the valuable nodes explored but missed category. Lastly, based on the attacks performed, the program outputs the true positives, false positive, and false negatives. True, true positives correspond to the successful attacks. False positives are the failed attacks where the uh, valuable data node is not correctly identified. And false negatives are the unexplored nodes. Which the random walks simply couldn't cover them, and the program never saw them. Now, based on these parameters, the precision and recall scores are also calculated. Next, we'll go back and see if our job is completed. You can see that the job has been completed. I'll quickly terminate my cluster so it doesn't charge me more money and go back to S3 in the program output directory. Now this directory, we can see that the YAML files have been added. We can quickly go to them. Let's see the sim scores YAML first. This is the sim scores YAML. The sim score YAML includes the uh, original valuable nodes, the corresponding put out valuable nodes, and the maximum sim score found. If I navigate through this, a sim score of 1 essentially means that the valuable node was not modified. In our case, we are using an attack threshold of 0.1. So for example, here in this example, 2782 is matched with 2782, which is a correct match, but the sim score is less than 1. This means that the node was modified, but because of our uh, SimRank algorithm, we were able to correctly match it and attack it. We will get more details about the attacks performed in the second output of our program. Let's open this one as well. This contains different statistics we just talked about. We can see that it attacked 3 nodes which had valuable data and were modified, and all 3 of these attacks were successful. This is primarily because of the SIMRAM. Contains different information too, which we just saw. Overall, The attacks had a precision of 1, the recall of 0.94. So that's all for this walkthrough. I hope you had a good time. Thank you. Thank you, everyone.